The tangent line problem and derivatives. The tangent line problem will be discussed in more detail on the next slide. First, let's review some vocabulary that you will need for a better understanding of what the tangent line problem is. First, the secant line. The secant line is a line that joins 2 points of a function. Second, average rate of change. The average rate of change is the slope between 2 points of a function. Another way of saying that would be the slope of the secant line. And a very short way of writing the slope of a secant line would be like this, m sub sec. So this is the slope of a secant line. Tangent line problem. The tangent line problem pretty much consists of this question: what is the slope of the black line? Now the black line intersects this graph at this one point right here. You can see it in red. But there is a line that intersects the graph there. What's the slope of it? And this might be a silly question in your mind, knowing from previous math courses that the slope formula is y2 minus y1 over x2 minus x1. And you know that there are 2 points necessary to find the slope, or in this case, on a function, an average rate of change. You need 2 points. Well, over here, there's only 1 point. How are you supposed to find the slope of a line if you only know 1 point? Using the vocabulary from the last slide, we will need to estimate the slope of this line using the slopes of secant lines. So let's give this point over here some coordinates. Since we don't have anything very specific about this graph, we can call this point C f of c. And that is because this red curve here is the function f. So I already mentioned that we need to use the slope of a secant line to estimate the slope of the black line over here. So in order to find the slope of a secant line, we must pick another point on the graph. Maybe about right there. So let's connect these 2 points and see what happens. Now that we've connected these 2 points, you can see that the slope of the secant line is not as steep as the slope of the black line. But we can still compute that slope. Let's see what that looks like here. So we picked this point over here that was h units to the right of c. So this total distance here is c plus another h is c plus h, so that is the x coordinate for this ordered pair. And the y coordinate for this ordered pair, you just substitute c plus h into the function. There we go. And we can find the slope between these 2 points. You can see that there's an x1 and a y1 and an x2 and a y2. So we can just substitute these numbers or these expressions into the slope formula. And when you do that, it looks something like this. So I used this point over here to be x2, y2, and this point over here to be x1, y1. And you can see that we have f of c plus h minus f of c all over c plus h minus c. And there is some simplification that happens in the denominator. You have a c minus c reduces away, and that leaves you with the slope of a secant line looking like this. F of c plus h minus f of c all over h. And you may have seen this before in a previous math course. This is called the difference quotient. And this is what we use to find the slope of a secant line, or another way to say the average rate of change. It's been a few minutes since I mentioned that the slope of this blue line is less steep than the slope of this black line. So it's not a very good estimate for this slope here. How can we get a better slope? To get a better estimate of the slope, you want to move that point closer to the black point. So instead of the point here, we're going to move it closer to the black point. Another way to say that is we want to shorten this distance of h that is between the 2 points. I want to shorten this distance from here to here. Now, as you can see, the slope of this green line is a better estimate for the slope of the black line. If we move the point even closer, you will see that you will get an even better estimate of the slope of the black line. So all of these slopes of the secant lines we are finding the same way. It's just we are changing where the distance of h. So this point is c plus h, f of c plus h. This point here, also c plus h, f of c plus h. So all of the slopes of these secant lines are being found the same exact way. It's just that h is shrinking. If you reduce h until the points are infinitely close, you have a tangent line instead of a secant line. The slope of a tangent line is the slope of the curve at that point. This underlined part of the definition, reduce h until the points are infinitely close, can be reworded in the following way. H approaches 0. We reduce h until the distance between the 2 points approaches 0. Well, the last time we talked about something approaching a value, we were talking about limits. So we can write the limit as h approaches 0 of the slope that we were looking for earlier, f of c plus h minus f of c all over h. If we have this limit of this slope, this is what gives us the slope of the tangent line. And then another way to represent the slope of the tangent line is m sub tan. On this slide, there will be some more vocabulary. Again, 2 definitions. The first of which is tangent line. If f is defined on an open interval containing c, and again c is a specific x value, and if the limit as h approaches 0 of this difference quotient equals a number, which means it exists, then the line passing through the point c f of c with the slope m, referring back to this slope here, is the tangent line to the graph of f at the point c f of c. And that's exactly what we were trying to figure out on the last slide. There was a point c f of c that would have been the black point, and we drew a line that was tangent to that curve. We just needed the slope to figure out the actual equation of that tangent line. And we figured out that the slope of the tangent line you find as you decrease that distance between the 2 different x values that were on the graph. The next definition down here, the instantaneous rate of change. Example, let g of x equal 1 over 2x plus 1. Our goal is to find the equation of the tangent line to the graph of g at -1, -1. And since we're trying to find a tangent line, and lines require a slope and a y-intercept, I think the first thing we should do here is find the slope of the tangent line. So the slope of the tangent line equals the limit as h approaches 0 of g of the specific x value we are trying to find the tangent line for, so -1. So g of -1 plus h minus g of -1 all over h. Now, in order to continue this limit, we need to figure out what g of -1 plus h is and what g of -1 is. So over here to the right, I'm going to write down g of -1 plus h. Well, up here in the function, if x gets replaced with -1 plus h, so does this x. Let me just write it down here. 1 over 2 times -1 plus h plus 1. So when you simplify the denominator down, everything becomes 1 over 2h minus 1. The next step is that we need to figure out what g of -1 is. And this is a little bit easier than working with evaluating the function with the variable. So g of -1, that is 1 over 2 times -1 plus 1, which is -1 when you simplify it all down. Now, if you notice over here the ordered pair, the -1, -1, we really didn't have to do this work to figure this out for this -1. That's what this ordered pair tells you. So if you look and you substitute -1 into the function for x, you'll get back -1 as the y value. That's exactly what we did, and we just proved that. So if you have a complete ordered pair and you're looking for the function at that x value, you can just look at the y value here. So this limit becomes the limit as h approaches 0 of 1 over 2h minus 1 minus -1 all over h. So you can see I just took this part for g of 1 minus h, substituted that in. I took this part -1 for g of -1, substituted that in. And now we just have to go through our limit techniques to see how this simplifies. Well, I see that I have a fraction within a fraction, so I want to multiply the top here and the bottom here by this least common denominator. And when you do that, you'll get a limit that looks like this. So here is the limit being multiplied in the top and the bottom by 2h minus 1. And when you actually go through and multiply everything by 2h minus 1, you'll get this limit over here. So then the last few things that need to happen here are the simplification of things in the top. So 1 minus 1 reduce away, which leaves you with a 2h over h. Let me write it out here. This limit as h approaches 0. This is 2h, there we go, over h times 2h minus 1. This cancellation of the 1's allows me to reduce the h's here, which leaves me with the limit as h approaches 0 of 2 over 2h minus 1.
And so now there's nothing stopping us from substituting this 0 in for h. And when you do that, you're left with 2 over negative 1, which is just negative 2. So there's the slope of the tangent line. Remember, we did all that to find the slope of the tangent line. The rest of it, we just need to set up the actual equation for a line, y equals mx plus b. There we go. And we all know the slope of this line, and we know an ordered pair on this line. So when you make all of these substitutions in here, you'll see that the 2 goes in for the slope. The negative 1 is for the x value. That again, that's from up here, this ordered pair. The negative 1 will also be the y value. So we come down here, negative 1 plus b. And when you solve this for b, you'll get that b equals 1. Now we know the slope via the limit process. We know the y-intercept via algebra. Now we just have to actually put the slope and the y-intercept into this equation. So our final answer here with the equation of the line tangent to the graph will be y equals negative 2x plus 1.
Example, let f of x equal x squared plus 4x. Find an equation of the line tangent to the graph of f at the point negative 1, f of negative 1. In order to work through this, we will need to be using the limit definition on how to find the slope of a tangent line. And also, we will need to figure out what is this ordered pair. Right now, it just looks like negative 1 and then whatever you get back when you substitute negative 1 in for f, or in for x in the function f. So to figure out this other coordinate, simply substitute negative 1 in for x and get back a y value. And when negative 1 is substituted in for x, a y value comes back that is negative 3. So the point on the original function is negative 1 comma negative 3. Now we need to find a limit. The limit as h approaches 0 of this, and I haven't filled anything in yet because you don't know what c is. I mean, kind of you know what c is, it just hasn't been labeled yet. So over here, that number negative 1 and that number negative 1, that is what the c value is. So in this first set of parentheses back over here in the limit, we need to have c plus h, which is negative 1 plus h, minus f of negative 1. And so what's really nice about this is you've already figured out what f of negative 1 is. It is negative 3. What needs to happen now is you need to figure out what f of negative 1 plus h is. And it's done very similarly to how you found f of negative 1, but instead of substituting in negative 1, you're going to substitute in negative 1 plus h. So over here on the right side, you can see that the x was replaced with negative 1 plus h, and so this x was replaced with negative 1 plus h, and this x was replaced with negative 1 plus h. And when you use algebra to FOIL this thing here and distribute the 4 and collect all the like terms, you end up with f of negative 1 plus h being h squared plus 2h minus 3. So let's rewrite this limit over here. So this limit becomes the limit as h approaches 0 of h squared plus 2h minus 3 minus a negative 3 over h. And as tempting as it may be to factor this, don't. it will not help you to factor this as you're trying to go through and find the limit. What needs to happen next is some simplification in the numerator. You can see that subtracting a -3, that's the same thing as adding 3. So now that you have this addition of 3, you can see that there's some cancellation that happens here, leaving you with the limit as h approaches 0 of h squared plus 2h all over h. And this is the part where we can get rid of the problem. And that problem being the h in the denominator, for the most part. The problem is the h in the denominator. Every time you try to substitute 0 in here, 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 you get to divide by 0. So to finally get rid of that, common factor the h out, you'll get a limit as h approaches 0 of h times h plus 2 all over h. Bam! Lo and behold, the h is gone in the denominator. We can substitute that 0 in there for h now, and we get a slope of a tangent line being 2. That being said, we are asked to find the line tangent to the graph. So we are not just looking for the slope of the tangent line. That's what this is here, m tangent. What we need is the line, the actual line. And I like to use the point slope form, which is y minus y1 equals m x minus x1. And that's because I have a point and I have a slope, so I can just substitute some numbers in here, and that is the equation of the line. So when I substitute these numbers in here, I will get a line that ends up being y plus 3 equals 2 times x plus 1. And that's because these coordinates are negative, and when you substitute them in here accordingly, subtracting a negative, as we saw over here, ends up being addition. Now, if you like slope-intercept form, if that's something you like, here is the equation of the tangent line in slope-intercept form. And now that I think of it, you will want to put your answers of any tangent lines in slope-intercept form. Horizontal tangent lines, plus a little review of horizontal lines. If you'll recall, horizontal lines have a slope 0. And when you look at these lines on any graph, these lines are flat. And this will be a big idea a little later on in calculus, but for right now we're just sort of laying the groundwork for what's to come. So horizontal lines have slope 0. So do horizontal tangent lines. So the horizontal tangent lines means that the slope of the tangent line is 0. And this idea is going to be pretty pertinent in the next minute or so. So horizontal tangent lines, what you will be asked to do is to find specific coordinates on the graph of a function where the horizontal tangent lines exist. And when you do that, you're trying to find a tangent line with a specific slope. And when you're doing that, you will leave C as C in the limit definition of finding the slope of a tangent line from before. Once you find the limit, you will set it equal to the slope you're being asked for. Usually it'll be 0, or the horizontal tangent line. So from the previous slide, when you're trying to find the slope of the tangent line, you know that the limit as h approaches 0 of f of c plus h minus f of c all over h. And when you're trying to find a specific coordinate on the graph of a function, then c will stay a variable. And you will set whatever that limit is, if it exists, you will set it equal to 0 if it is a horizontal tangent line, or you'll set it equal to whatever slope you need if it's not a horizontal tangent line. But again, we're going to concentrate on the horizontal. So when we find this limit with c's still in the limit, we will set it equal to 0 and be solving for c. Let's take a look at an example. Example: find all points x, y at which the graph of f of x equals 3x squared plus 12x minus 1 has a horizontal tangent line. The first thing you want to recall here is that a horizontal tangent line has a slope of 0. And since we're looking for the slope of a tangent line, we need to use this limit in order to find the slope of the tangent line. Now, as stated in the previous slide, these two c's will be the same. Remember, c represents a specific x value. And since we're trying to find an x and a y, or maybe multiple x's and y's, we need to just leave these c values right here. So the first thing I want to do is over here on the left is find what is f of c plus h. Well, over here in this function we have f of x equals all of this, but f of c plus h is going to represent something different. X gets replaced with c plus h. So in the right side of this equation, all of the x's will get replaced with c plus h. So then all we have to do is some algebra here. We'll have to square out this c plus h. That'll require some foiling, so that'll be c squared plus 2ch plus h squared plus 12 times c plus h minus 1. So the only thing that happened between this first line and the second line is that this was FOILed out. The next step, I will distribute the 3 to all the terms here and the positive 12 to all of the terms here and get 3c squared plus 6ch plus 3h squared plus 12c plus 12h minus 1. And that's it. That's the furthest we can go with this first expression in the limit. Now the second expression is a little easier. Since we are subtracting f of c, all that needs to be done is to substitute c in for x in all of these places. That looks like this. You get f of c equals 3c squared plus 12c minus 1. So now all that's left to do is to substitute this up here in for f of c, substitute all of this in for f of c plus h, and take the limit. From the previous slide, we are trying to find this limit as h approaches 0 of f of c plus h minus f of c. And when those red and blue boxes from the previous slide get substituted in for f of c plus h and f of c, it looks something like this. F of c plus h equals all of this in red from the previous slide, and f of c equals all of this in blue from the previous slide. Now some really nice things happen here. Let me get a different color. And that is, you'll notice that because of this subtraction right here, terms will start to reduce away in the numerator. And if you look, you're subtracting a 3c squared, but in the front here you have a 3c squared. So 3c squared minus 3c squared reduces away. Also, this will happen with 12c minus 12c. That will reduce to 0, and negative 1 minus negative 1 will reduce to 0. And that's really nice. Every term that only has c in it is canceled away. And that leaves you with the following limit. Here we have the limit as h approaches 0 of 6ch plus 3h squared plus 12h all over h. And one thing that I should be mentioning throughout this example is that if you try to substitute 0 in for h in this original expression up here, you'll end up with the indeterminate form 0 over 0, which means that we can simplify this somehow. And so all these steps where we cancel any terms that are constant or have c only, that's the first step into simplifying this entire limit. The next step in this simplifying this entire limit is to factor out h in the numerator. If you'll notice, after you reduce all of the c terms and the constant terms, you're left with terms, all of them have h. So that allows us to common factor out an h in the numerator, which allows us then to reduce the h in the numerator and denominator, giving us a limit as h approaches 0 of 6c plus 3h, there's no square here, plus 12. And with this final limit here, we can use direct substitution to substitute that 0 in for h and get that the limit is equal to 6c plus 12. Now we're not done. We have this c left over in our expression, our answer for the limit. And in order for us to find the specific x value c, where this function has a horizontal tangent line, we need to take this expression, 6c plus 12, and we need to set it equal to 0, which is our desired slope of the tangent line. And when you go through and solve this for c, you'll get that c equals negative 2. And that is only half of the ordered pair that you will need to get the final answer. The other half of the ordered pair comes from when you evaluate the original function, let's say f of negative 2. When you evaluate the original function at negative 2. Negative 2 minus 1. And when you crunch all these numbers, you get negative 13, which would be the y-coordinate. So there's a horizontal tangent line of the original function f of x at the point negative 2, negative 13.
On this slide, you'll learn a little bit about physics, being just some vocabulary and notation. So for here, s of t, this is a notation borrowed from physics. The function s is the position function. The next function that you'll see down here, v of t, stands for the velocity function. But if you're trying to find v of t, you just take the derivative of s of t. And lastly, a of t is the acceleration function. And in order to find a of t, you will just need to find the derivative of v of t. And one thing that you want to know about these velocity and acceleration functions is that they are instantaneous rates of change, which means they tell you exactly what's happening at a single point in time. The next bit of information down here is the average velocity. Average velocity happens over an interval of time, not at a single point in time, but just over an interval of time from A to B. This is the velocity, is the change in position over the change in time, which looks like this. We start at B, or the later time, we find where the position is, and then we subtract from it the position at time A over B minus A. And we call this average velocity because this is an average rate of change. And in order to find the average rate of change, you just use the slope formula. Change in y's over change in x's. And the last little bit down here is that if you're ever asked for speed, speed is the absolute value of a velocity. So velocity is what's known as a vector, which means it has a direction and a magnitude, where speed has no direction. So if you're ever looking for speed, find the velocity and make it positive. To the examples. Example: a baby drops her rattle off the Empire State Building at a height of 1,250 feet above the ground. The rattle's height above the ground t seconds after it's dropped is s of t equals 1,250 minus 16t squared. How fast is the rattle falling at 4 seconds? Since we are given some information about the position of the rattle as it's falling, and we are asked to find how fast the rattle is falling after 4 seconds, we will be finding the instantaneous velocity here. And you can know that we are trying to find the instantaneous velocity because there's only one time value given here, and that is 4 seconds. So to find an instantaneous velocity, we will need to use the limit formula that looks like this. The limit as h approaches 0 of s of 4 plus h minus s of 4 all over h. Now this is something that you've done in that you've seen in a few examples previously. I'm going to give you a chance to pause the video, try figuring out this limit all by yourself. It's just when you see this example, the first step is to set up this limit. From here, you just need to use this function. The first thing that needs to be done here is that s of 4 plus h needs to be evaluated. And when you substitute 4 plus h in for t, and FOIL this binomial out, and multiply everything inside by negative 16, and combine like terms, you'll end up with this right here. The next step is to evaluate the function s of t at t equals 4. So this is a little easier. All you have to do is come over here to the function and substitute 4 in for t in both places. And when you do that, you end up with 996. So it's this green information here minus S of 4, which is 996. And you can see pretty easily from this point that the 996 minus the 996 will reduce away, leaving you with terms that only have h in the numerator, which is good, because now we can factor out one of those h's. So this will be h times negative 128h minus, oops, not h, minus 16h all over h. And now the h in the numerator and denominator cancel. And what we are left with is the limit as h approaches 0 of negative 128 minus 16h. So now you are able to substitute directly in and get that how fast the rattle is falling after 4 seconds is negative 128 feet per second. And from the previous slide, you know that speed is the absolute value of that. So that means this is the velocity of the rattle after 4 seconds, and that makes sense because we are talking about the rattle's height above the ground after so many seconds. Well, the height above the ground as the rattle falls toward the ground is decreasing. So the velocity is negative 128 feet per second, whereas the speed at which the rattle is falling is positive 128 feet per second. Final example. What is the rate of change for the area of a circle with respect to its radius when the radius is 11 feet? Well, we're trying to figure out some idea about the area of a circle. So we know that the equation is A equals pi r squared. And we're trying to find the rate of change for that area when the radius is 11 feet. So using the idea in the last example, I only see one instance here instead of the question being what is the average rate of change between 9 feet and 11 feet. Nope, we just have one number to work with, and that number is 11. Another way to write this function, this area function, is that the area is dependent upon the radius, and the area is calculated as pi r squared. So this will give us a setup to go through and help us figure out the evaluations that we'll need here in a second. Now the limit as h approaches 0 of a of r plus h minus a of r all over h would work just fine, but we have this number 11 that we need to substitute in for this radius. So the limit is actually limit as h approaches 0 of a of 11 plus h minus a of 11 all over h. So by a similar process of the last example, we will go through and figure out what this, evaluate the function at 11 plus h, and then we will evaluate the function at 11, and then do the limit simplifying techniques, and I will reveal the steps on how to get the final answer. All right, so here is the final answer after you substitute 0 in for h. This whole term goes to 0 and you're left with 22 pi. Now, one of the things that you will want to keep in mind is that while you're working through these problems, you'll notice that we said that it was 11 feet. That's what the radius was, 11 feet. Well, what are the units of this measurement? Well, since we were trying to figure out the rate of change of an area, this means the units here will be feet squared, or squared feet. So the final answer here is 22 pi square feet.